Okay, so now that we've defined nucleophile and electrophile, I think it's worth pointing out that these terms, nucleophile and electrophile, can actually very easily be confused with terms such as acid and base. To be fair, it's easy to confuse these terms because molecules aren't actually restricted to just using one of these descriptors. So, for example, we could have one particular molecule, and this particular molecule could potentially be described as a nucleophile, or it could potentially also be described as a base. So let me give you an example. So this is hydroxide. So hydroxide right here, and if you remember from the last video, we had hydroxide we described it as a nucleophile. But we could also have this hydroxide and interacting with stuff, and it could potentially be described as a base. So as an example, let's go ahead and put H plus in solution, and we could describe how hydroxide could potentially interact with this acid. So let's go ahead and say if we combined our hydroxide with our H plus, what we would get. And it's obvious at this point, hopefully, that if you have an acid and a base, you can combine this acid and this base together to give you water. So we could have H2O. So in this case, it actually makes a little bit more sense to describe hydroxide as acting as a base instead of acting as a nucleophile. And if we took hydroxide and we threw the hydroxide in with, let's say, this carbon electrophile, so this positively charged carbon with this positive in the center carbon. In this case, the hydroxide could still interact with the positively charged carbon, but at the end of the day, you get a slightly different outcome. So in this case, you have the oxygen forming a new bond with carbon. So now, for the bottom case, if we had the hydroxide interacting with a positively charged carbon, and we're going to make this new oxygen to carbon bond, we could use this arrow notation to give a mechanism for how this works. And we could show, our nucleophile, starting electrons right here and ending electrons on this carbocation, this carbon with a positive charge. In this case, it makes more sense to describe the hydroxide as a nucleophile and the positively charged carbon as the electrophile. Because in the past, when we talked about acid-base reactions, in the Bronsted sense, the base always removes a hydrogen, and then the acid donates a hydrogen. But in this case, that's not actually what's happening. So the use of the acid-base descriptors aren't really that useful. We could still draw the arrow notation for the top example, just like we did for the bottom. And the only difference is really that for the top example, the hydroxide is attacking a hydrogen instead of attacking a carbon. So it's really doing the same kind of thing. We're just using a different descriptor for how the hydroxide is acting. To try to make this a little bit easier, one metaphor or analogy would be if you wanted to describe why this hydroxide could either be described as a nucleophile or a base. The analogy is that you could take, me, for example, and the way that I interact with, let's say, a family member, let's say my mom, is going to be different than the way that I interact with, let's say, a student. I'm still the same person, it's just the way that I act differs depending on the situation. And it's the same thing with this scenario below. So the hydroxide can potentially act as a nucleophile, or it could act as a base. It just depends on the scenario that's happening.